Good afternoon, everybody. We are here together. Okay. Good afternoon, everybody. Do you hear me now? It's not working. No.
Now it's working.
Okay. Good afternoon, everybody. We are here gathered to listen to this seminar, where the speaker is Peter Bechtold from ECMWF. ECMWF is the European Centre for Medium Range Weather Forecasts, and is an international organization at the level of UNESCO, more or less. So it's not, let's say, something that is made up from European community, but is funded also by European Commission right now, because there is the Copernicus initiative. Dr. Peter Bechtold works there since 2000, more or less. Okay, he's a meteorologist. He's a PhD in meteorology, in geoscience, I think geophysics, from Clermont-Ferrand, and he has before a degree from Karlsruhe, so he's German origin, and he stayed in Reading, where ECMWF is based since many decades. Now he's moved to Bonn because the European Centre moved a part of it in Bonn, okay, and in Bologna, where there is the new supercomputer, the Atos supercomputer, high-performance computing facility. Okay, European Centre is producing not only forecasts, but many other things, among which I mention all the reanalysis, which are the information we have daily from media about climate change. So all the information we have are coming from Copernicus right now, but the main source of everything is the model that is producing this forecast and these informations, a bunch of them. I cannot describe even in a very broad way all the work of ECMWF, because it's really huge. But the main point today is to understand a little bit more why this forecast is so good, because it's the best in the world. I can say this because I was in the States, and we know that European Centre and the model that is at European Centre is the best in the world, and is used also by Americans and by all the other countries that are inside the European Centre, which are 27. Inside these countries there is Switzerland, there are countries that are not inside the European community, but they all the same are inside the ECMWF. So Peter Bechtold is one big part of this model, and the big part is the most important part is the forecast of what we call a convection, so precipitation. I will trivialize the idea that is behind all this, but convection is one of the most important part of every forecast we do, generally speaking, and Peter Bechtold taught the ideas that are behind this and realized them inside the model. So it's a great honor to introduce Peter Bechtold and to listen to his ideas about what is today describing about forecast.
Can you hear me? Yeah. So thank you, Paulina. Thank you all for coming. I'm very glad, and of course I'm very grateful to Professor Paulina and Bruno for the invitation, and for Miriam and Lorenzo for all the work together and the help. And because I'm very grateful to visit the beautiful city of Perugia, with also the beautiful churches. This is my home village, and but we also have an old Roman. So old Roman Benedictine monastery, and this recognizes as a storch that brings children and brings luck. So for me, it was not so easy when I thought, what can I tell you? Because everything is lean. It has to be a bit general, but it also has to be a bit special because technical, and you cannot avoid this. And I know when you have a small group, it's very difficult to compete with all the others. And I think what all you do is very good, and even you have to be even stronger than the others, because it's a small group, you have to fight and to make a place for everything. Yeah? So this is even, I think, more difficult than the work I have when you have at the time we were 200 people, now it's 500. This is getting a bit crazy, but then well, you just there's a big machine. So we started a little bit with climate because Carnival 10 was here 2022. In the meantime, it's getting even warmer. This is 2024, and you see the whole globe is actually red, so it's warm. And it was not even El Nino year. So El Nino is when you have the warm waters in East Pacific. So this is not the case. You see, it's a bit cold. But there's one region, this is around Iceland, and the Icelandic people actually, they complain since a few years they are colder, and this is because they have more northerly flow, and it's also maybe expected that the Gulf Stream might change and bring even more northerly flow. So they suffer already a bit from cold actually. And if you put this a little bit in perspective, what happened since 1850, so you have these historical records, and you know Lorenzo have a project working on these historical records. This is very important. And so between 1850 and 1920, so there's a bit more uncertainty in the observations, but not much, 0.1, 0.2 degrees. And then you see, since when we go from 1960s and we put through all this smoothing curve, well, it's pretty certain it goes up. And in the last 30 years or so, it's even went up by 1 degree. It was 24 was the first year getting over the 1.5 target, and you see there's a bar, so 0.2 degree deviation. It doesn't look very positive in that sense. Yeah. So this for the climate. And behind the climate is the circulation. But in the meantime, everything is getting faster. We had the revolution of machine learning. Everything is getting faster. And this is just to show you the evolution of the forecast quality here measured in terms of winds in the tropics at 1500 meters. And it's since 2002, more or less, when I arrived. And so all the models in this operation center get better. The red one is the IFS, this is the European Center model. And so we were quite happy, so we can continue like that, try to get just ahead of the others above. And you see what happens. In 2020, the first one was Pangu, the Chinese machine learning model. And then the big tech companies like Google, Microsoft kicked in, and they're also producing weather forecast using our analysis. Yeah. And so you have to do something. You cannot just sit. And then the AIFS, artificial intelligence IFS, was developed, and you see this the gap between a physical model and the machine learning model is quite big. This is nearly 1 day in forecast quality. So this doesn't forecast only a certain set of variables, but this is quite amazing. And we see at the end we can more or less marry these two. Yeah, I will come back to the machine learning just at the end. So I try to give in 45 minutes, and so don't worry if it's too long. So first, something about predictability and in general, and we have to see this global, and we have to see this in the tropics. This is was a completely different project. We looked at the diurnal cycle, but first we plotted the climatology of precipitation from the observations. This is this. And you see in the tropical convergence zones, West Pacific, Indian Ocean, where there's on the globe essentially it's raining most of the time is there all the precipitation. And these are different models, and this is run for 20 years. Blue means too much precipitation, and red means not enough. And you see all the models have similar errors, and this was specified as SSTs. If you have coupled to the ocean, then it's even more difficult. So why is this? Why do you see if you have too much precipitation in the Western Indian Ocean, you are too dry over Indonesia. So then we look at this. Some of you might know Franco Montini. He worked at the Center for, arrived a bit after me, and he retired now, and I think he's in Bologna now, yeah. And he was still working as a consultant and published this memo in 2024. So what he did is, so we take, this is also a way in geophysics, a very good analysis method. So he took the average precipitation over this red box, over the Indian Ocean. You take the average precipitation, and then you compute from this point with all points on the globe. So every day, or every monthly mean, or every day, what is the precipitation on the correlation between this precipitation and the precipitation at another point? You can add a correlation, or you can plot what is called a regression. So it's similar but not the same. So you plot the time series of the precipitation in this red box, and as a function of the time series of the precipitation of each individual point, and then you make a regression curve, and the results are more or less similar. So then, what you see is that if you have a lot of precipitation in this red box, you are dry at over the Indian over the West Pacific, Indonesia, and so on, and you are wet again in the East Pacific. So this is how the precipitation is linked east-west over the tropical oceans. That's not all. Yeah? So you can even now plot the correlation or the regression of the precipitation in this region with the sea level pressure in the northern hemisphere, or the 500 hectopascal geopotential. This is, and this is here you see Europe. So what you see is that if you have a lot of precipitation there in the Western Indian Ocean, Central Indian Ocean, you have over the Mediterranean high pressure, so drought, and a lot of precipitation in the North Atlantic, so Northern Atlantic oscillation in negative phase. Yeah? So these things are very much linked. Yeah? So tropics is linked to the mid-latitude, so that's not all. So how does this information propagate? So propagation is mainly east-west on the globe, but there's also in the meridional direction, not much, but this propagates along a grand circle. Yeah, so waves propagate in this sense along a great circle. But essentially the information is east-west, and you will see at the end the machine learning information is also coded in a way that is more or less only along the line. And you can also do this in the models, and you see that if you do a two months forecast, this is the season forecast, you can download the 3 months forecast, and you see that that's the same correlation, but the correlation for this signal to tropics good, but the correlation to the signal in the mid-latitudes is not so good. And this is also one of the reasons why seasonal forecasts are actually quality is quite mediocre, because you cannot correctly more or less, but not correctly, the amplitude of these stellar connections. You lose this information. So this is this point. Now we talk about ensembles. So we do a forecast, and at the same time we do it, say 50 times, because the forecast quality is getting worse in the future. But you need to know you have the value of the forecast, but you need to know the uncertainty. Is it certain or uncertain? Yeah? And for this, we do ensemble forecast, and until 2023, we did 50 members at 18 kilometers. And now we do 50 members at 9 kilometers, and we even do every day 100 members, so this is this extended range forecast for 46 days. And now we just want to see what is the influence of the resolution, what is the influence of the ensemble size, does it matter? And we go again back to the tropics. And the first thing is you need a good climatology. If your model doesn't can reproduce the observed climatology, then it's useless. So we take the precipitation observation. This is GPM satellite. This is, I think, now quite standard now. You see this tropical land here, tropical oceans. And this is the day 2 forecast, just the unperturbed forecast. This is the day 15 forecast. And this is the ensemble mean of the 50 members, low resolution, high resolution, and the 100. So climatology, they all look more or less okay. Not as much synchronized in the observation, but broadly climatology is okay. Day 2 and day 15, they are still okay. Now we look at something else. Now we just plot every day, concatenate from the observations every day the rainfall variability. And this is plotted here. And you see it's maximum over tropical land globally. And we do this from the day 2 forecast. Broadly, yes, but there is underestimating the variability. And now what we do, we have the ensemble members. We have 50 members, and we can, day plus 2 forecast, we can take the standard deviation of the spread between these ensemble members. Yeah, take this. And you see this is very small, day plus 2. Because the uncertainty is small, so the spread should be small. But now, if we go to the day plus 15 ensemble forecast, the spread between the members, we calculate 15-day forecast, take it every day in the precipitation and just look at the spread between the members. You see is nearly equal to the day plus 2 and nearly equal to the climatology. Yeah? So by day 15, you reach the climatology, and the uncertainty has to grow. So the uncertainty, so the spread has to be more or less equal to the error, otherwise it's not a good ensemble. So this is this, and it does it, but it had to be shown. And now another thing is that we look, for example, this where we use these precipitation observations, this is what we have available. And we look also at the wind error at day plus 5 and the day plus 15. And then we see that at day plus 15, the error is much larger in the subtropics, in the mid latitudes than in the tropics, which means that the predictability in the tropics is better for longer range than we have in our European weather. And this becomes even more clear if you look at the precipitation forecast as a function of time. This is 20 days, and this is done. So here is this one is the correlation, starts at 0.5 in tropics, so not too high. Slowly goes down, and this is called the CRPS. So this is, if you evaluate ensembles, this continuous rank probability score is a measure of the distribution, and you can read about this, but it's generally used to evaluate some probabilistic forecast. So the distribution has to be the how far the distribution is from the observed distribution. And there we see that the high resolution, the 9 kilometer, this red, is for precipitation. Resolution for surface variable is better than the 18 kilometer. Surface variables is horizontal resolution is important, but if you go beyond 15 days or something like this, it doesn't matter anymore. So this 30 kilometers as good as 9 kilometers, because then the information is lost. However, now if you go to the northern hemisphere, so this is the black one, and this is only a control forecast. The black one is the precipitation now in the northern hemisphere winter, and we see now the correlation is much higher, 0.7. This is good. Northern hemisphere summer is much lower already, only 0.5, start 0.5. So it's convection. It's much more uncertain. And this is the tropics, winter and summer. But we see that by day 10, the tropics, the northern hemisphere has lost its predictability. Tropics is as good, if not better, than the northern hemisphere beyond day 10. And one of the main drivers of predictability is called the Madden-Julian oscillation. This is a 30 to 60 day oscillation. And you see this big cluster, a few thousand kilometers of convection that suddenly pop up and then slowly propagate to the east. And you see some rotation, this big vorticity at 850 hectopascal, and this will spin up sometimes some twin tropical cyclones in the tropics. So now you see we have plotted this. How can we analyze this? So we take from the satellite observation the outgoing normal radiation and plot this as a function of time and longitude. And this is called the Hofmüller diagram. This is here from the satellite observation, and this is from the model forecast. Forecast concatenated every day, the day plus 2 forecast. And more or less, it looks very similar, and you see these stripes, some go in this direction, and some go in this direction. So these are really waves. If you want to visualize these waves, we just plot the anomaly, just subtract the mean in space and time. Then we have plus is dry anomaly, and blue is convective anomaly. And then we can make a 2D FFT, Fourier analysis, and then filter this analysis in space and time. And then we get here this kind of waves. This is now the MGO. So you see these bigger low frequency clusters, and these are called Rossby waves, propagate to the west, and Kelvin waves to the east. And now we can look at the forecast of these waves as a function of lead time. So day plus 2, day plus 15 of a Rossby wave and of the MGO. And you see MGO keeps the phase, but the amplitude gets a bit smaller. And for the Rossby waves, so amplitude very good, but you get random errors in the phase. Yeah? And with this varies the predictability of the precipitation and the tropical winds in general. Yeah. So how can we improve further this extended range 46-day forecast for the mid latitude, which is difficult. So now there's one more concept, and this is called reforecast. So we do every day 100-member 46-day forecast, every day 100 members 46 days. But in addition, we run twice a week, or twice a week or a day, a very small member ensemble, 5-member ensemble, for that day, starting with that day, but for the last 20 years. So let's say day, but for the last 20 years. And then what we look at is the anomaly of the actual forecast with respect to this climatology theory forecast. To say this is really anomalously warm day, week 2, week 3, or whatever. Yeah. So it's calibrated. And so we only show these anomalies. And so we use this reforecast to do it once and correct just for the bias, and then nudge the actual forecast to this bias corrected reforecast. We do it twice. It's very expensive, but we just want to see what can we do. And the technique we will use, and we will see at the end, we use this also for machine learning, some nudging, and we use temperature and vorticity. And because these are spectral variables, we can filter them spectrally to wave number 0 to 21. see, this is very clever, and this is an important thing. Yeah, so we only filter this to wave from 0 to 21, and you use this. In few words, the result is that if we nudge to the polar regions, then this is the improvement. You see week 3, week 4, we get a bluish means better. Week 3, week 4, improvement in the Northern Hemisphere forecast. We don't see anything. If we nudge the polar region, we don't see anything in the tropics. If we nudge the tropics only, we will see a small improvement in the tropics and also some improvement in the Northern Hemisphere week 3, week 4, but not too much. And for comparison, this is the whole forecast improvement we achieved since 2004. So a bit everywhere and mainly in the tropics. And this we could achieve if we had optimal bias correction via nudging in the polar regions. Yeah, polar regions, one of the most important for us. Yes. Just on this is a bit present. So actually, this I worked on when I was at the center mainly on convection. So we need to get the nighttime convection right. As I showed you, we had these tropical waves, the human cycle of convection, and then also the shortwave radiation. And this is also an interesting thing. If you go this morning we had 4. But sometimes if you go to the more Arctic regions or in the southern hemisphere storm tracks, you have, even it's minus 20, then you will have ice crystals falling. But on top of these clouds, you will have liquid water. So we constantly produce, if you want, fog. Yeah? But then these droplets freeze and fall down as ice crystals. But on the top remains a liquid layer. And this is very important for the radiation budget of the Earth. So to get this, and you see this especially here in the storm track regions and here in the southern hemisphere storm tracks. These liquid layers on top of ice is actually we also need to get this wrong. And altogether, Meteorforms also introduced the same convection scheme we developed, and this is the forecast improvement they got when they introduced this, just for comparison. So, but there are things that still need to be done. So one is we worked on this African sprawl lines. They propagate. You see these big systems. They propagate the observations. They propagate to the west. Before we didn't have anything. Now we have it more or less right. And it was told that if you use explicit convection, 2 kilometer resolution or 4 kilometer, then actually we get things that are too noisy. But is there still something missing? And hopefully I will get this in before I retire in 2025. This is some advection, and I'll show you this now. So these are model results from several European models. And you see this is precipitation. What do we think is the some models are WOM, some models is ICON. You see which is the one with parameterized convection, which one is the explicit? What would you guess? The lines, yes. You see these strikes. These strikes, you see it's on the radar observation. So, as Miriam said, so this one is the parameterized, and you see this. You have problems to do this advection of showers, but the explicit models and high resolution models, they often these showers they just live too long, so you get too much precipitation. You don't dissipate. You get these stripes. You get a bit overdone the stripes, but you want to get something in between. And then we introduced also the advection, and the Israeli Met Service, they always complain that this is the observation, but this was the IFS forecast, so the precipitation was stuck at the coast. Now we take more advection of snow into account in the convection, and we can get the precipitation also on land. But it blurs a bit more. So this is now in test phase. I hope to still get this in. And this is just another case, and I think we can skip over. So towards, I said already, high resolution model was said this will solve everything. A lot of money. Climate groups, they say Hamburg and so on. Even Destination Earth was built on that. Yeah. So this will solve, but it's not the case. So what is obvious that you improve precipitation over orography. So this is the Italian example. So these are the observations and co-values here, the Alps and here the coastal mountains. 9 kilometer 4, 2.8 and the Alps. Over the orography in general it gets better because you better resolve the orography and the flow over it. So, but more or less, this is more or less already most of the story. But there are other things. We also produce now visible satellite images, and this is Nadia view, so a vertical, no night. So these are sequences every 3 hours. And we focus now here on the East Pacific or Peru region, and you see these anticyclones in the clouds, and it changes a lot from hour to hour. And this is the GOES observation. And we zoom a bit in. And this is another day, actually. And this is the observation, and this is the model forecast. And the dynamics is doing these clouds overturning. And you see the structures are way too big. It's something like, I don't know, 100 kilometers, but this is just a few kilometers. So why is this? We don't know. There's no solution yet for that. And this is 9 kilometers. So we can say, oh, okay, try that. 1.4 kilometers. We can do this in this. It looks similar to big structures, but the nature structure is much smaller. And there you see there's one thing, is this line here. And then when we had this first, we thought that we made a mistake. But actually what it is a gravity wave propagating out of the Andes. And it's very deep gravity, and this has one phase is sinking motion. And this is more or less deterministic and propagating out, and you see it also in the observations. And we're quite amazed about that. So, tropical cyclones will be okay. 4 kilometers, you need 4 kilometers will be okay. This is the observation radar. This is the convective rain rate. You see the arms, convective arms of the tropical cyclones, and the core is a vortex, more or less saturated. And yes. And 9 kilometers. So now come back to the ensembles. Here we have the central pressure in the tropical cyclone. Dark black is the observation, and this is the maximum wind speed. And these lines are the ensemble members. And before this summer, in June, we had what is called perturbation, was stochastic physics tensor perturbation. Every member was the total physics tensor we perturbed stochastically. And now we perturb the parameters instead, so this allows to change the amplitude of the heating, of the friction terms, and also the vertical profile. And you see that now the ensemble is what we want, is that the solution, the actual solution is comprised inside what the spread of the ensemble is. And Medicanes is same story, and then a nice article by very young and Lorenzo, you can have a look. And this is just a summary, but this is 4 kilometers against 9 kilometers. What is red is worse, and blue is good. So we are not there yet. We cannot run 4 kilometers yet. We're still working on it, but it's not just that it gets better. And the main reason is shown here. The main reason is that, so this is the observation, you see Meteosat over the Indian Ocean, and the GPM satellite rainfall. This is what we currently have. And if you run, we switch off the convection, or with the resolution, you see these big blobs, and this is unrealistic. You get these big blocky blobs. However, what we see here, what we currently still have, this problem, we get these rings. Yeah? So, gravity waves are natural solution of the shallow water system. If you throw a stone in the lake, this is what happens. They are there, it's part of the solutions, it's okay, but they're much more damp in nature, and it's a bit because the parameterization is forcing, and the dynamics has to produce the quasi-trostopic response. The response, it takes time. So then there's some disequilibrium and it produces these waves. And we don't have yet a solution for that operationally, but we are still working on that. And this is just shown here. This is another case, you see this. Can happen, especially in tropics. And this is called the dispersion relation of gravity waves. So you can, for example, just measure then the wave number and the frequency. So just the signal every 30 minutes or something, and then you have the frequency. It's about 1 to 3 hours. The distance is something like I think it was something like 600 kilometers. And then you go into the dispersion relation for gravity waves, and this is the vertical wave number. Phase speed will come out as omega over k, what you know from physics, and the phase speed is 50 meters per second. So it's like a tsunami. The faster the wave is, the deeper the wave. Yeah. So this goes to 10 kilometers in the atmosphere. So the fast waves are deep ones, and so this is a gravity wave dispersion relation. So I can finish in 10 minutes. Is this okay? Yeah. So the last part will be this. The last part will be a bit the last 10 minutes, and then you're free machine learning. Yeah, to relate this. So machine learning models are coming fast. What are they doing? And are they physically consistent? And now the main technique is this. This is open source now, this Animoy project, and how do we do this? And also the big tech firms, they use the ERA5 analysis, reanalysis, train it for the last 30 or 50 years. Yeah. And then in addition, you can also use the high resolution operation analysis for even better training. And what we use now, and what Google is also using, Angel, is this graph neural networks, but also the language machine learning part, the great language models are using. So you have something like nodes, and you have edges. So this is how this node connects to the neighbors. Yeah. And as an input, you just with Python, PyGraph, or PyTorch, you have this. You can produce these graphs. Yeah. There's automatic graphs. It has to be on the sphere. We are on the sphere, so it has to respect the topology. And then what you do for the training, you go to some lower, if you want, low resolution or hidden layer. That so this is an encoder decoder. You go to a smaller dimension problem, and then you decode it, and you go back to the original grid. So you get back the output on the input grid. Yeah? And this is done for several variables, and not all, but on pressure levels. And this is the scorecard, and you see it's mainly blue. And it's actually, I was a bit shocked because we worked so much on precipitation, these topics. And this is the machine learned precipitation from the reanalysis. So actually, what the model is doing, but and this you gain 1 day. And this now is and this what is 2 meter temperature, and this is this. The orange one is the best. This is this Aurora from Microsoft. They use even the 0.1 degree. And currently we only use 0.25 degrees. And the important point is, so what the machine learning model is doing is only steps of 6 hours. Yeah? So it only trained on the 6-hour forecast. you want, and then auto regression to the next 6 hours, the next 6 hours. If it had small time steps, it would make more errors. This says just one step to go to 6 hours. We can't do this in the model. But because we have a lot of operations, this is one reason why the model is also good work. But the other is even more complicated. Machine learning knows a bit about the physics. It's all subject physics, orographic drag, heating. This is all subject. It doesn't need to know this. It only knows this from the information on these nodes. Yeah? But in the model, we have to reinvent what is on the subject happening. And there's so it's using this information indirectly, but without having to do the work, actually. And that the fields, that you can see that the fields are actually quite realistic. So this is the analysis. A big storm, I think it was 2 weeks ago, over Ireland with wind speeds of more than 40 meters per second. And this is the IFS. You see that this is smoothing, but the picture is quite good. But it's smoothing. They don't get the extremes as in analysis. And because I talked about the MGO, is this big clusters, this 46-day forecast, actually is not much better than blue one than red. I was happy about that a bit, and actually at the time we gained 6 days by improving the convection. So while the model is a bit thinking, you can do also succeed. But now you're on a level, then it gets really difficult to improve further. And you need, obviously this machine learning is a big machinery to do optimization, which you cannot do by hand anymore. And also, when the people started, somebody was employed by us to machine learning only for the radiation. He gave up, it never became operational, but he is the head of the machine learning team now. And what you train is the whole model. You don't train individual things, you train the whole thing. Because when you put this in the model, you are limited by things like the time step dependencies and like this. You are limited, exactly, you get limits. Like this is a bit different story. So, and just 2 words, two more things. Okay. So now there are even more crazy ideas. There's people that one new section is forming. You train only the observations. You take the 2-meter temperature, the satellite observation, and predict the observation 6 or 12 hours later, or even 5 days later. And because I told you that you have this encoder-decoder, you can have the output at any output of the specified output grid. That means you can predict at any location, actually a radio sound, something like that. But the quality of, then you don't need a physical model at all. Currently, you still need a physical model to use the analysis. Otherwise, you can run any machine learning model easily. So, and this brings me to the last point, is there's the good news also for us and for everybody is that you can marry both. And this was brought up by, and there's a very recent article by the Canadians Met Service, and they will put this operational, is that, so you have your analysis, you run machine learning model, but it's so fast. This forecast takes, I don't know, 1 minute, something like 1 minute or 2 minutes. And then you can filter this. This is the clever thing. It has to be like that. With the spectral model, you can filter temperature, and you for TCT wave number 0 to 21, this machine learning forecast, and use this to relax the temperature for TCT field, so the wind field of your forecast to the forecast from machine learning. But only the wave number 0 to 21, that is everything that is bigger than I think 2,000 kilometers, something like this. You relax to that. Only the very, very large scales, very large synoptic scales. And so you use both. And the physical model has all the variables. So sunshine, has everything, so many variables. And you keep the high resolution. So you have all the advantages We also did this as Ina Polischuk, my colleague, is doing this, and you see this scorecard is also blue. Not as blue as I showed you before, but it's still a 5 to 10% improvement. And the advantage is that you improve the tropical cycle forecast because the wind is better than the position, but you don't deteriorate the structure because you keep the small resolution. Yeah, so this will come soon. I think maybe still this year, but I think it makes everybody happy. And then I keep, and then just for a summary, then last time, every time there's somebody presenting, I ask the same question about machine learning. But what do you learn? Why is the machine learning model better than the physical model? And what is the source of the error in the physical model? And you cannot get any answer. Nobody thinks about it. So it's up to you. And my thinking was, this global angular momentum balance. And this was when my habilitation, this was the one professor from Denmark, he asked me to couldn't answer this question, but I never forgot it. And if you think about it, so if you see that what we saw that the tropics and mid-latitudes, they improve both. But you know that tropical winds are easterlies and mid-latitudes are westerlies. Now from physics is if you slow down the tropical easterlies, so if you speed up the tropical easterlies, you need to speed up the mid-latitude westerlies because of angular momentum balance. So if you improve one, you will improve both. And the residual of this is this meridional circulation. What we learned is the heavy circulation. This is a residual, it's very small. And this residual of the big winds is just this meridional circulation, it's very small. So this error is so important and it's so difficult because it depends on the friction on the mountains. There's two places where you lose. It's on the friction by the mountains, friction on the ocean surface. And globally, it's 2.5 watt per square meter. And this is also the energy you can use to, this is the energy you can extract in the whole globally for the wind farms, for example, 2.5 watt. And this is the order of the error. This is the order of the error here. And with this,
thank you very much for this very enlightening and difficult talk for everyone else, even for people who science those things, because you showed a lot of things different and altogether they are a lot to take in. What do you want? Are there any questions? Yeah. I think there are some questions.
What you discuss in terms of the prediction in a few days?
yes.
In terms of water resources management, we would like very interested in prediction for some months, 2 months. What about the performance of what do you think about it? Is there any chance to see to a manager in the next 5 months the water level in the aquifer within this?
Yeah, so didn't bring it, but so for Europe, if you look at the, unfortunately for the tropics we have been begun, but for Europe, weeks 3 and 4, we are very close to climatology in the forecast. And this is especially true for heavy transportation. There's a small signal in week 3, but week 4 there's nothing. So unfortunately, especially for water management, the catchment is
Okay.
This was also one of the reasons why the extended range forecast they went better. In week 2 was useful. Week 3 started to get, they wanted this every day. Before we had it only twice a week because there is some signal, but we also this changes a lot from day to day now still. for the range, but beyond 2 is not so much.
So the question around errors.
Yeah. And of course, it has to you have to use full ensemble. It's usually to see what you do, but still, it's not. It's also important for you that there is some. Will there be more than some?
I have more of a philosophical question. Because, first of all, if you, I don't know if you can go back to the other slide, but you showed the improvement of this machine learning method, and I wanted to know, is it improving, because I didn't see this spiral, is it improving also for precipitation?
You see there, but it's not doing any precipitation. So the precipitation uses precipitation, is trained on the precipitation of the analysis and of the operation forecast. This precipitation is actually a 6-hour precipitation, not a 6-hour forecast. So it's trained on the forecast. It's trained on the 6-hour precipitation forecast. It's not producing any precipitation or physics in itself, but so each variable in this list, in this machine learning context, are so-called prognostic variables. So so they're trained on a 6-hour step, but then prognosis means auto-regressive from the next step to the other. We can also have some diagnostic variables. But this is crazy things that actually is a 6-hour forecast. So this trend. But because that it learns to know about the correlation with the other variables, and then for longer ranges it actually gets better. But for the very short range, this is the pure machine learning. Should be worse. You see here. This was the nudged one, and this is the pure machine learning, so total precipitation. So this is the RMS, or the correlation with this F-status, I don't know, but one of these skills at the beginning you see it's worse. It's only at the end because circulation gets worse and you normally forecast it.
So for the longer range. But my question would be because I think also we talked about it last year, 2 years ago about it, because the Google team had just come to ECMWF to work on this machine learning. So what is the future for forecasting? Meaning that if we have this, because we showed the first graph that the error for some fields is decreasing with the use of machine learning, but the machine learning needs still the model data.
Exactly.
So
fortunately.
Can we still do the thing like we should?
Cannot do anything without the model, but we have one new group that is very clever people. I don't know anything about that. So this foundation model to learn only from observations, and they just start what is called here, what I learned just 2 weeks ago. Forgot this. This weather generator. This was just going to be formed. I don't know what this is. With a new class of foundation machine learning models that should work more like large language models, and the aim is to get like this only learn from observations to get rid completely of the physical. But this nobody knows when this will be, and but I hope still we always need. And the physical consistency is a bit of interesting. But this is
Thank you, Peter, for your presentation. And speaking about physical parameterization of the models, so in this transition going into a kilometer scale, what do you think is about your experience? What do you think is the most difficult parameterization to adjust for this transition, or are all they all they have the same role. Because, for example, I think at the friction at the surface. So maybe I would say, in my opinion, because I like more maybe, or because I see more that it's easier to change is the surface flux or the turbulence concentration. And what I don't know about microphysics and radiation, so I want to hear
You told everything already. Actually, when
I was.
when you're over the Alps, you're completely right. When you're over the Alps or Himalaya, then the biggest thing is orographic drag. And actually, the problems with this throttling, we had to filter because you get much more gravity waves. And then they break, and they're slow, they break. You get too many gravity waves, they break in the jet, and then you slow down the flow. And you get bigger errors. So you need to, how to treat your orography, you need to be more careful. If there's no orography, then all the sensitivities is then in the microphysics. So yes,
Okay.
you have to be more complicated and
And another small question, because
Yeah.
I'm working in the ocean friction through analyzing direct numerical simulation.
Yeah.
Very small pieces of ocean, like meters. And well, the Earth is covered by 70% of ocean. So if I ask you about what is the most relevant, the ocean, the friction from the ocean, or the friction from the land in your
should we discuss with Anton Bellas and
or also
so the orographic drag is probably the most important for the flow because it's in the region where you have it impedes on the strong wind fields, so the jets. But the surface wind, so the drag, is mainly influencing the fluxes. So also the heat flux, especially the moisture flux. And in the tropics and the low wind speed regime, is still not clear how you define the moisture flux. And because this moisture flux then projects on the convection, and then you get the influence directly on the deep troposphere. So I would say in tropics it's a surface flux, and if you go to mid latitudes where strong winds are, then this is orographic. Yes.
Thank you.
I've got a very simple question. In the blue sentence written there, is there a question mark at the end?
Yes, and this can be done lessons for the physical models should read like this. And
I was wondering.
There can be, in principle, the physical model should do as good as the machine learning model because it doesn't invent anything. It's just from the analysis the physical model has produced. So it should be possible. It should be possible. So just one last word, and when we do data simulation, so every 6 hours new observations come in and correct the forecast. And you can already learn in principle from that, also like the machine learning model. But nobody tells you what you should do. You should notify surface fluxes, drag over the ocean. That's no.
I have a question for Professor Camito, who is an expert in artificial intelligence and machine learning. He embedded and so the degree is anything similar to what you showed in your experiment at the nano scale? Is an expert.
No, actually, no. I simply spent time writing on forecasting.
Yeah.
So using physical models.
Yeah.
And so we studied the limits in forecasting by using physical models, and also slightly we dealt also, of course, with atmosphere, climate, weather forecasting, this kind of problems. And the idea is that, okay, machine learning is, as you correctly pointed out, is based on the search for correlations.
Yes.
As we, of course, trivially know correlation is not causation, and then there are a number of very strong theoretical issues for which you can do that up to a certain point. When you train your network, the goodness of the training depends on how large is your history level.
Yes, yes.
And usually the history is never large enough in order to get good prediction in the long range. That's only just a consideration. I'm certainly sure that you can, using machine learning, can learn lesson or errors of the physical models. Still, in my humble opinion, physical models should be the guidance for drawing prediction.
I agree with you completely.
I'm sure you do. Thanks.
Any other question? No?
Thanks a lot for the presentation. I have a question, maybe it's a bit irrelevant to the presentation, but it's still about the presentation. I had an experience when I was in Germany, we were working on the catchment in the western of Germany. I had a problem with I'm hydrologist working on the runoff, or forecasting the runoff. I had a problem with the noisy precipitation. I don't know if we can call it the noise or if it's like the inherent fluctuation of the precipitation. But the model, the LSA model couldn't capture the sequence of the data because of this inherent fluctuation. How do we call it? Is the noise like the random noise or the white noise that is like with the high frequency noises, or it's just inherent of the precipitation?
Precipitation, especially summer, is inherently noisy. Model is also noisy. And the only way is some probabilistic approach and sufficiently large ensemble to handle the noise. Otherwise, I don't know anybody who can, any other method to handle the noise at the moment.
At the end, we could handle it. I know that we could handle it because we used decomposition methods for decompose the time series to the different frequencies, and then we modeled at each frequency at the end. We just reconstructed different frequencies at the end it works. I can publish the paper. But my main question was that is this the noises associated with the diversification, or this is the inherent fluctuation of the diversification? Because it was very noisy, and in my point of view, maybe it was the noise. I didn't know exactly the source of the noise.
Which purely observational, or was it also?
Yes, it was observation. The point was observation from the CDC, from the climate center.
Yeah, precipitation is probably apart from wind gas, is probably the noisiest variable you can get. Wind speed is noise. Wind speed, if you look at fluctuations or precipitation, inherently turbulent. So yes, this is the most local one. You can plot several variables as a function predictably, but if you want noise, precipitation is the noisiest.
Any other question? I have one question about modeling, because I'm fond of models, and I don't understand very well from what you have shown and what you know. What is the right side to face the increasing resolution of models? So it's better to increase the resolution of integration, or it's better to get rid of many degree of freedom and simplify for some part of the equations of the processes?
Yeah, it probably depends on the life cycle of the phenomenon you want to look at. the larger the phenomenon, the larger domain size.
But you have shown different results also with the machine learning that make you see that, in time, maybe it's better to enlarge your space in time and
this is maybe this only because it needs much more training, and actually the forecast you produce precipitation every hour. So for hydrology or catchment, you need to at least every hour 30 minutes, or this is not done yet. If they could do it's just because the analysis are only very 6 hours, but you could do more. And it might not be better if you do the machine every hour. I think this is it's good that this is like that, because then you have the model for doing the really fine scale you need. I think it's
I want your speech. Thank you.
yeah, done.
Okay, for anybody who's online, there are other seminars following CLC seminars. So, Center for Climate Change, Research in Climate Change, we organize other seminars that will be announced to the channels we have used also in this case. So we will see names and also another channel, and on this channel we will give the training of the seminar. So if you want to listen to them, please connect and be in touch with us. Okay. Thank you. Thank you for
Non ci sono 15 persone all'inizio, adesso sono 29. L'unica cosa che mi chiedevo è